So let's close out this short chapter by just discussing briefly about what can be done. Essentially, glacier melting, marine ice sheet instabilities, and various calving processes, and so on. They are not processes which are very amenable to geoengineering approaches, right? It's not like you iron fertilization of the ocean or sprinkling dust in the stratosphere to reflect sunlight or carbon capture and sequestration and so on. These are open systems which are out of control once they start. So you can only do indirect things like bending the curve and slowing down the warming, especially of the ocean. And even that you cannot do directly. You have to reduce the greenhouse gases and short-lived pollutants, super pollutants, and wait for the ocean to adjust to the new atmospheric warming and additional energy. So here are again looking at the projections out to 2100 for the various scenarios. We talked about these before, but just in case you don't know, representative concentration pathways RCPs were designed based on the net additional forcing at the top of the atmosphere. So you have shortwave energy coming from the sun and long wave energy going out. If they are not in balance because of the increased greenhouse gases and albedo changes because of land use and glacier melting, then there is a net additional forcing. Those are designed with various options of decarbonization. We will see those in a minute. So net forcing of 2.6 is the benign one, which can bring us to the possibility of staying below 2 degrees centigrade with a certain probability and with a certain range, as you can see here, 0.9 to 2.36, 2.3 degrees centigrade. And there are many models used to do these and many scenarios of population increase, technologies, renewable options, and so on. And you can see 116 scenarios, 509, and so on and so forth. So different RCPs have different number of models simulating the scenarios. So RCP 4.5 is obviously higher, and it still keeps us from a range of 1.7 to 3.2. And these plumes around them, around these mean thick lines, are the potential range. So 0.9 to 2.3 is this range, and here it's 1.7 to 3.2. RCP 6 gives you 6 watts per meter squared additional forcing at the top of the atmosphere. And the business as usual scenario of RCP 8.5 basically takes us into places where we don't want to go in terms of warming. With respect to 1850 to 1900, it gives us 3.2 to 5.4 degrees centigrade, and you can see the range there is quite large as well. But we are, historically speaking, on that track already in 2014, but even in 2020, where we are now, we haven't really bent the curve yet, because we haven't even started effectively mitigating the short-lived climate pollutants or switching to enough renewables. There is increasing renewables, electric vehicles, various command-based regulations on industries, transportation, etc. But we are still on this trajectory, so we are in a desperate need to bend the curve very quickly. Range of CO2s that would result here, these are emissions in gigaton CO2, and the atmospheric concentrations, this will be greater than 1000 ppm, 720 to 1000. So to reach 1000 ppm, we have to go back to the time of the dinosaurs, when Arctic had no ice, Greenland, Antarctica, everybody was ice free. So if it has happened before, why should we worry? Because we are not used to that kind of CO2 and temperature. So that's the main thing. So during the Holocene, the temperature changes have been basically very small, order 1 degree. So are we capable of dealing with greater than such great warmings, even with all our technology? right? Instances like COVID, for example, show us the limitations of technology as well, right? Entire humanity was brought to its knees by COVID. Only now we are beginning to get vaccines, and we will maybe forget about this in a few years, but maybe not, right? So you will find various approaches like this for decarbonization, and much has been written about how hard it is to decarbonize because the system is right now completely designed to be dependent on carbon-based fuels and energy. So we need a complete redesign of the entire system to be able to switch to renewable energy systems. And we talked about energy technologies, merging transportation, and worrying about dealing with intermittency of the renewables and so on. But we have a long way to get there, right? So it's a matter of how quickly we can accelerate. So this is one example from the EU, which talks about the 5 pillars of a decentralized, decarbonized, and digitalized energy landscape. So by all means, by all understanding, energy system needs the biggest and the fastest decarbonization. That's the root cause. So the energy intensity of the GDP and the carbon intensity of the energy need to come down very, very rapidly. So here are the pillars. Low carbon energy system, a transition architecture is needed to go to a low carbon energy system. An optimal energy mix with an increased integration of renewable sources and alternate fuels. We talked about this in the grid design as well as the transportation design and the smart grids, microgrids, nanogrids, distributed energy production, including hydro energy production with dams and so on. What's the word? Anyways, solar, wind. Okay. So increase flexibility while maintaining reliability and performance. Data analytics to anticipate demand patterns and empower users. So this we talked about in terms of smart grids and nanogrids, and combining utility scale control versus local controls, and virtualized power plants. So we won't go into the details here, but this is going a little bit from ice melting and sea level rise into the whole problem, because controls on glacier melt, ocean warming are not easy directly. We have to do it through decarbonization. Okay, so hydroelectric, that's what I was trying to get at. Hydroelectric. Okay.